Hi everybody, in this video we're going to take a more formal look at transformations, something we've done a little bit when looking at quadratics and looking at cubics, like turning point form effectively. But now I want to sort of formalize what we've discussed and give you language and processes in order to apply transformations to any old function, not just those two, although that's where we're sort of at in our unit of work at the moment, looking at cubics. But you can see here I've got an example off to the side. It's f of x equals the square root of x. I know we haven't done the square root of x as a graph, and it doesn't really matter. The important thing is that transformations occur as a result of applying each transformation to a parent function. And you just need to know what that parent function looks like. So the parent functions we've looked at so far are f of x equals x squared and f of x equals x cubed. They're the parent function, and then we apply transformations to them and note the effects. Okay, so we're going to have a look at the transformations and use this parent function to see what the effects are. I've chosen this parent function because its shape is quite unique. I think it sort of, for the most part, you can see what's happening when you apply these transformations. Okay, looking over here, so transformations are from a base or parent function. They don't have to be. You can take any old function and transform it, to be honest. But typically, we start from a base or parent function, and then we build up transformations on that parent function. There are three categories, as you should be aware by now. There are dilations, there are reflections, and there are translations. And we'll look at these in turn and use our example function to see how they go. So in a nutshell, dilations are stretches or compressions towards an axis. Okay, so each point in the function is either stretched away from an axis or compressed towards an axis. It's not a movement of the function. It's each point is either scaled up or scaled down. And I guess it's probably a good time now, excuse me, to talk about that. Transformations changes what the graph looks like. It's very visual, but ultimately what's happening is that every single point in the function is being transformed to a new position. Sorry, instead of saying point, I'll say coordinate. Every coordinate is being transformed. So a coordinate that's there may find itself up here somewhere, or down here somewhere, or over here somewhere. So to track what effect a transformation has, you can often pick a point like 0, 0 or 1, 1 or something like that, and see where it lands, see where it ends after the transformation has taken place. So you're picking a point as an example, knowing that every single, infinite number of points along here are being transformed in a similar way. Okay, transformations affect one of two, parts of the function. So if you think about it, there are kind of two parts to a function. There is the input, whatever you're putting into the function, okay, which is normally x. And then the whole of the function is what is output. So, as a machine kind of thing, we're inputting x we're applying some sort of rule to it called f, and out of it comes f of x. So with transformations, we are either changing the input or we're changing the result of the whole output. So it either affects the input, i.e. we replace x with a new expression, or we're changing the output, i.e. we're replacing all of f of x with a new expression. And we're going to build on that in a second. But let's just have a look at these dilation, stretches, reflections, and translations, just as a brief example. So a stretch or a compression. So first of all, if I put a 2, I'll leave that one there. I'll type in a new one. We'll use this new one as our transformation. So at the moment, they're exactly the same. The blue and the red are the same. But if I put a 2 in front of the square root of x, I've now dilated this function. And what you'll see is that 0 for this graph and 0 for this graph is exactly the same, because I haven't done because when you multiply 0 by any number, it's just 0 again. So there's been no stretching happening at all. But if I go here to 1, 1, only because it's the easiest point to look at, what I've done is I've taken square root of x, which is the whole of the function, and I've doubled it. So this is a dilation of the output. It's a dilation of the whole function. And so the value of 1, 1 times 2, becomes 2. This one here was 1. It is now 2. So what was 1, 1 is now 1, 2. Okay, so the x output, so the x hasn't changed, but the y has changed. So we can see that this graph is stretched away from the x-axis. Okay, so it's a dilation away from the x-axis of a factor of 2. Similarly, let's see if I can find a nice one like this. 4 has at x equals 4, on the base function, we have y equal 2 because the square root of 4 is 2. But on the new function 2 root x, that value 2 has been stretched by a factor of 2. So 2 times 2 is equal to 4, and hence the new point is 4, 4. Okay, so that's what it does. Putting a 2 in front of the whole of this function here, the whole of the parent function, has the effect of doubling every single output value. Every output value, what was here. So if I just pick any random point here, I don't know what it is, I'm not even going to click on it. That point there, if I double it, I'd get that point there. That point there, if I double it, I'd get that point there, and so on. So that's what that dilation does. In a similar vein, if I go 0.5 root x, then I'm halving the output values, the output. So remember, it either affects the output, the whole of the function, or the input, just x. So here, where I have 1, 1, I've now got 1.5. Okay, because this one has been halved to here. If I go over to 4, then square root of 4 is 2, but when I halve the output, it's now equal to a half. Sorry, 1, beg your pardon. So it's been halved. Every single value has been halved. 0, 0, half of 0 is 0, and so that's why it starts, it's fixed here. Okay, so it's been scaled rather than shifted. Okay, now what we haven't looked at before in great detail is what happens if we instead dilate the input. And you might want to pause the video for a second, and I'm going to put 2 here in a second, and you might want to wonder what happens if I would double the input. Okay, hopefully you paused it. I'm going to hit 2. And it's probably not immediately obvious what's happened, but this value here, 1, is now found over here at 0.51. So because we are affecting the input now, we've replaced x with 2x. Okay, it's a replacement of the input x with now 2x. What we've done is we've accelerated the growth of the graph, so that although in the original graph it took you all the way, you had to wait until you got to 1 in order to get the square root of 1, which is 1. Now you only have to go as far as a half to get to an output value of 1. So this has accelerated the graph. It has in fact compressed the graph towards the y-axis. Okay, so when it gets pulled towards the y-axis or pulled towards the x-axis, it's called a compression. When it gets stretched away or stretched away this way, it's called a stretch. Okay, generally it's called a dilation though. So we would say, as you can see here, that it's the factor is not actually 2, but it's a half. It's 1 on whatever this number is here. Okay, so we would say that this function has been dilated towards the y-axis by a factor of a half, 0.5. Okay, and again, just to show you, just for the sake of it, excuse me, the value of 4, which gave an output of 2, halved is now 2 to give you an output of 2. Okay, so the output hasn't changed. It's still 2 here and 2 here, but the input has been halved. Okay, so that's dilations, stretches and compressions. And importantly, we have this idea that we have an input, and an output. Okay, we need to treat them separately. So with an input, the value that you see on the graph is just the dilation factor. But when you have it on the for the output, the dilation factor is just, say for example, A. But for the input, the dilation factor is 1 on A. Okay, because of the way it operates. Okay, so that's covering dilations and an introduction to transformations. Just mindful of these videos being too long. What I might do is I might stop the video here and start a new one looking at reflections and do a third one on translations, and then look at how that all ties together. So what would be worth doing now is, once this video is finished, is firing up Desmos yourself. Maybe try it with an x squared graph and an x cubed graph. Play around with that. Not only remembering that there are two kinds of, well, if you like, there are two pathways for dilations, a dilation of the input and the dilation of the output. And then there are two kinds of dilations. There are stretches and compressions. And play around with those so you can get a good, strong sense of how these dilations have an effect. And I'll see you for the next video soon.